Like if you don't remember, if you don't remember 3 presidents ago, that's fine. You were like 5. All right. So basic exponent properties. When you're multiplying the same base, this is x to some power times x to some power. That's the same as x to what power? I was assuming we would all be like confident and resounding in an answer together. 10, yeah, that's right. You're just adding the exponents. All right, what about that second one? X to the third to the seventh. You have a power to a power. This is going to be x to what? I heard one person say 21. Does anyone agree with that? Yes, I agree as well. 21, you multiply. The way I always keep this straight is when I see parentheses, like in between the 3 and the 7, what operation does parentheses typically mean? Thank you. Yes, it means multiplication usually. Like when you like distribute something into the parentheses, we multiply. Same kind of idea with exponents. At least that's how I always keep that straight. Oh, it's outside parentheses. When I distribute it in, I multiply. All right, this one right here, it looks kind of like that second one, but we had to keep in mind that there are 2 separate bases. The 2 is separate from the x. So since both of those are being raised to the 7th power, we have to raise both to the 7th, kind of like by distributing that exponent to the exponent spot for each of those bases. Now, the 2 doesn't have an exponent yet, so it just gets that 7. The x already has an exponent, so how am I going to combine those two? That's right. We multiply them just like we did in that second problem. So then this would be x to the 21st. So make sure if you've got multiple bases in there, right? That's 2 to the first, x to the third. That 3 is only on the x, not on the 2. And you can leave it like this, or if you do raise 2 to the 7th, you'd get 128, x to the 21. Same thing. You're good to go. All right, next row. We are dividing. And when you divide exponents, you would subtract, but then you'd be left with a negative. So whenever I see like a division or a fraction, what I always do is I ask myself the question, where are there more x's, on the top or on the bottom? Let me just look at the numbers. Where are there more x's, everybody? On the bottom. So I know that my final fraction will only have x's on the bottom. As to its exponent, you then ask yourself this second question, how many more x's are on the bottom than on the top? There are 4 more, right? Because 7 is 4 more than 3. So that's x to the 4th. Now, what about up top? We generally never have a fraction with nothing above it. So what number can I pop in there? Yeah, it's a placeholder. We would just use a 1. So this is the same as 1 over x to the 4th. We want it written this way because it's a positive exponent. If we use the other rule where you subtract exponents, well, 3 minus 7 is a negative 4. You'd have x to the negative 4th, and you'd have to flip it into the denominator. You'd get the same thing. All right, this one right here, negative exponents. We also kind of mentioned this yesterday. It came up, or last week, Friday, these came up again. And we never want to have a negative exponent in our problem. And so we can always just flip the base that has that negative exponent. We can just flip it to the other side of the fraction from top to bottom. Or if you have a negative exponent in the bottom, you could flip it up to the top. You just switch the side of the fraction it's on, and your exponent switches signs. But now, the important thing here is there's definitely a negative 3 exponent. We're going to have to take care of that. But what moves to the bottom? Is it just going to be the x with the 3, or is the 2 going to travel along with it to the bottom? To help you think about this, go back to this problem. Was that 2 and that x, was that the same thing, or did they each have their own separate exponents? They had their own separate exponents, right? That's like a 2 to the first, x to the third. Same thing down here. This 2x to the negative 3. That negative 3 is only on the x, not the 2. We could write this as 2 to the first power, couldn't we? Like just putting a 1 up there for its invisible exponent. 2 to the first power is just a 2. So that 2 does not have a negative exponent, meaning we don't want to move it. We want to leave the 2 exactly where it is up in the numerator. So that stays right there. Only the x would move, and its exponent would switch signs from a negative 3 to a positive 3 when it flips to the other side of the fraction. So we would want to leave that one as 2 over x to the third. Finally, everybody, anything to the 0 power equals Yes, fantastic. That's just a 1. Does not matter what's inside there. If the whole parentheses to the 0 power, it all equals 1. All right, that's a nice little review of exponents. I wonder if this is going to come into play at all in today's lesson. Probably not, right? These are usually always just like funsies to wake up in the morning for your great morning. Not your good morning, your great morning. So we have one more learning target, and it's going to be solving exponential equations. And this is the most useful like application piece of why we're using logs in the first place, how they're relevant. And we're going to see some real world situations. More so on Friday and Tuesday next week, we're going to get into some of the word problems and true applications of it. So for now, we're going to start with just a basic equation, right? So you don't have to read the word problem and try to interpret what's the rocket's height or whatever. No, that would not be the same thing, because dividing both sides by 2 doesn't work. I can't divide this by 2 because it's 2 to the x, not 2 times x. If it were 2 times x, then yeah, you can divide to cancel out that 2. But this is 2 raised to the x. It's a little bit different. So today we're going to start off by solving basic exponential equations. And we've seen exponential equations a lot over the last week and a half. It's an equation where the variable is in the exponent. And we learned about something called a log that we can use to solve for an exponent. But today's lesson is going to be the slightly easier way, where you don't have to use a log all the time. Sometimes you're going to get a problem that's easy enough to solve just by rewriting it as an exponential equation slightly differently. Does anyone know what the answer to this equation is, by the way? 2 to what power equals 16? It's 4, right? You just multiply 2 a bunch of times. You get 2, 4, 8, 16. So we already know, just looking at that, we're like, hey, x equals 4. If you look at an exponential equation like this, like on a test or something, and you just can think about it and be like, oh, x is 4, that's fine, right? This is simple enough. I know you're all are capable, logical thinkers that you can just be like, oh yeah, that's 2 to the 4th, so x would have to be 4. I'm fine with that. But what about something like this? You're solving for the exponent, for n. And here, I don't really know right off the top of my head. I could think about it a little bit and guess and check. But here's a better way to think of this, a better way to solve this. Notice that on both sides of this equation, look at the bases. 3 to some exponent equals 3 to some exponent. If both sides have the same base and they're equal, what do you think has to be true about the exponents on both of those bases? They would have to be the same also, because if they're not, just for example, if I had like 4 to the 5th equals 4 to the 8th, like, is that true? Could that ever be possible? 4 to one power equals 4 to another power? Does that make sense? No, clearly 4 to the 8th, that's going to be much, much bigger. That's not true. The only way for an equation like this to be true would be if it's like 4 to the 5th equals 4 to the, well, the only other possibility would be 4 to the 5th, right? The base is the same. Those exponents must be equal as well for that equation to be equal. But the cool thing is, in a situation like this, 3 to the 2n equals 3 to the negative 3n plus 1. If both of the bases are the same, then we can essentially ignore those bases. It doesn't matter what the bases are. 3 to what power equals 3 to what power. All I care about is those exponents. Because whatever one exponent is, I know the other exponent is going to have to equal that exact same number. So what we can do if we have the same bases, kind of like our log equations we did yesterday, when you had the same log on each side, you can kind of cancel out the logs. Here, if you have an exponential equation with the same base on the left and the same base on the right, you can just ignore the base and just say, well, then this 2n, that exponent on the left, it's going to have to be equal to negative 3n plus 1, because both of those 3's would have to be raised to the same power, so those have to be the same power. Anyone feel confident in solving an equation like this? Yeah. Go ahead, see what you get. Nice. Yes, you did. You're doing great, Brenna. Keep up the good work. So like we'd want to move the ends to one side so I can add 3n. So this is going to be now 5n equals 1. What would be my last step here, everybody, to get the n by itself? Yeah, you divide by what's in front of the n. That's a 5, so I'm going to divide both sides by 5. So those cancel, and we see, hey, this n equals 1/5. Boom. Is it okay for an exponent to be a fraction? Have we ever seen those this year? Right? We have. We've seen rational exponents, so that's legitimate. We know that it works. There's a way to figure it out. All right. That's our lesson for today. Yeah. So to see what is that actual exponent, you're totally right. If I wanted to figure out what is this original exponent. But in general, when we get an equation, we're not solving for the entire exponent, Ben. We're just solving for the variable. And we solved for the variable. We learned that, hey, if I plug 1/5 in for n, the left side will equal the right side. And you can double check that. If I plug in 1/5, this would be 3 to the 2/5. And this would be negative 3/5 plus 1. That also would equal positive 2/5. So it would be 3 to the 2/5 equals 3 to the 2/5. So we can verify to say, yes, that is the correct answer because it makes the original equation true. So it is the solution. But you don't need to tell me what that exponent is. We're always just solving for that unknown variable. Good question. All right, I've got 3 practice problems for you to try right here. And you'll notice that all 3 of them, the bases are the same. Okay, so all you're really doing for each of these is you're setting the exponents equal to each other and then solve for the variable. All right, let's see what you can do for these 3. All right, so every one of those bases are the same in each of those 3 different equations. So you can essentially ignore those bases and just set the exponents equal to each other. Take like 1 more minute. By the way, it is okay if you get 0 for an answer. 0 is a number. Also, sometimes you might have a sideways 8. Sometimes these are solving equations. There might be a no solution, or there might be an all real numbers. Those are also possible answers for these problems. Got some special cases. Smart man. All right, this first one. 1 minus x equals negative 3x, right? Both of the bases are 4, so I can ignore the bases and just set the exponents equal to each other. To solve this, I'm going to bring the x's all to one side, so I'm going to add an x to the right. That leaves me with 1 equals negative 2x. To solve for x, we're going to divide, and we see that, hey, negative 1/2 equals x. Anyone get negative 1/2 for the first one? That's wonderful. Good, very good. All right, this next one, when we set those exponents equal, you get negative 3v equals 2v. Now, this looks a little strange because there's only one term on each side, and they both have v's. But our goal is always to get the variables together on one side. And so I can add 3v to the other side. Now, when I add 3v to the left, well, what's a negative 3v plus 3v? Like, what number does that actually equal? That's a 0, right? So you can actually put the 0 right there, equals 5v. Now, don't say no solution, because there is a solution. Remember, you're trying to figure out, hey, what? You want to get that v by itself? Well, I can divide by 5 then. Like, if this were another number, like if that were 10, you would still divide by 5, right? So keep on following that problem-solving process. Cancel out the 5s. And 0 divided by anything is just what number? It's 0. So we would say v equals 0. And that is an actual solution. That is a value that it can equal, because 0 is a number. So you wouldn't say no solution. You'd say no, v is a 0 in this case. The last one's kind of weird. Negative 2a equals negative 2a. Now, just like that previous problem, I want to get all the a's on one side. So I'm going to add 2a to both sides. So I'm going to add 2a. When I do that, just like over there, we got a 0. But here, when I add 2a, I also get a 0. Does that mean no solution? Not necessarily. The variables are gone, but is that a true statement? Does 0 equal 0? Yeah, so what's that mean in general for the solution to this problem? We would use all real numbers. We'd say that a could be any number. If I plug any number in for a, that equation will be true. And if we look at this original thing, doesn't this left side equal the right side exactly? So if I picked any number for a, like 2 or 10, whoa, hi there. Like if a were 10, then this a would be 10. And wouldn't those be the exact same thing still? Right? I'd have negative 2 to the negative 20 and equals 2 to the negative 20. Same thing. I could plug in 2 billion for a. They'd both be the exact same thing. So basically that means it doesn't matter what I plug in for a. Any number is going to work. There's any number I can plug in for a, and that'll be the correct solution. It'll be make it a true statement. All right, now here's where the warm-up comes into play. We're not always going to have just one base equals one base. We can have multiple bases. And just like our warm-up, we would use our exponent properties. The first warm-up problem you did, we had x to the 3rd times x to the 7th. And when you had that, you would add the exponents together. So in this case, on the left side, you have 6 to some exponent times 6 to another exponent. So we'd want to combine those two bases together on the left, which we are allowed to do. Whenever you're multiplying the same base, we add the exponents. So I'm going to take this 5x plus 1 and add the negative 3x to make it like a new exponent. So it's going to be 6 to the, we have 5x plus 1 plus this negative 3x equals 6 to the negative 1. So I just added those two exponents because that's one of our basic rules. Like x to the 3rd times x to the 7th is x to the 3 plus 7. You add them. Now I can actually simplify this further because I've got some like terms. So we'd say, oh, that's 6 to the, I've got a 5x minus 3x. That's going to be 2x plus 1 equals 6 to the negative 1. So all we did is we used one of our basic exponent properties to combine those two bases on the left from having two sixes to being a single six. Now it's just like those problems you did in that first example. You've got 6 to some power equals 6 to some power. We can ignore the sixes at this point and just set those two exponents equal to each other and then solve for x. So we would say, all right, that 2x plus 1 would have to equal the negative 1, right? If the bases are the same, then the exponents must be the same. Subtract 1 from both sides. 2x equals negative 2, and x equals a negative 1. Are we okay with that concept? Hopefully it does draw upon those older exponent skills. All right, let's practice this. Try this one on your own, see what you get.
That's not even hard.
Shh, we're practicing new skills. Be nice. I made this easy to kind of build up your self-esteem and your self-value with completing these types of problems.
My 5-year-old brother can do this one.
Stop it. It's not nice. We have quite a few slides left. And if Gavin understands anything about the way I teach, he knows what's going to be coming. Are you scared? Did you get this one? It's pretty nice, right? These aren't bad. What? You think it can get more difficult than this? All right, so they've got the same base on the left, so I'm going to write it as a single base, but I'm going to add the exponents. So 3x plus 2x equals 5x. So now that they have the same base on the left, single base on the right, they're both the same. I can ignore those bases and essentially just set those two exponents equal to each other. So 5x equals 20, right? Then we divide by 5, and we see that, hey, x equals 4. Anybody else get 4? Fabulous. Oh, that's great. Good, good, good. Any questions on these steps yet? Nice. All right, let's see what else we have. All right, so this is just working with a different exponent property. When we had the same bases, we added exponents. Here, though, I've got 4 to the 3x to the 5. How do I combine the exponents when they're outside of parentheses? Do you remember? What operation should we do? Yeah, we multiply. So go ahead and try this one now. They're going to multiply the exponents on each side to combine them. So in this parentheses, you combine the exponents by multiplying them. Just write it as 4 to the, and what do you get when you multiply those two together? With the x. It's just going to be multiplied. So like 3x times 5, you'd write that as just 15x. And now here, to multiply, you can just distribute that to each of those. What'd you get? Nice. Yeah. Yeah. Yeah, good deal. Keep going. That's right so far. So you, when you distribute the 5, what's 5 times x? Okay. Otherwise, your steps are correct. Okay. After that, if that were, but so yeah, you know what's going on. So right here, this 5, you have to distribute it to both of those terms. Okay. So that'd be a 5x. All right, just make sure everyone, the only issue I've seen with a couple students is make sure you distribute that 5 to both terms on the right. You know, when you're multiplying a monomial times a binomial. So we'll have 4 to the 15x equals 4 to the, well, 5 times 6 is 30, but then 5 times a negative x is negative 5x. So at this point, we've got the same bases. And we can just set the exponents equal to each other. So 15x equals 30 minus 5x. Get the x's together on one side, so I'm going to add 5x to the left. That's going to give us 20x equals 30. Then our last step would be divide by 20. So x equals 30 over 20, and I can simplify that fraction just by dividing both of those by 10. So ignore those zeros, and x equals 3/2. Anyone get that? 3/2? Wonderful, wonderful. Very good. This is a pretty easy lesson, isn't it? All right, here's where you have to actually think a little bit. When you've got this equation, but you don't have the same base on each side, right? 2 to something equals 16. Well, I can't just cancel out a 16 and a 2. Those aren't the same values, right? 2 and 16 are clearly different numbers. So whenever you see a different base, look at what the bases are. So I see a 2 and I see a 16, and I'm thinking, do those both have a common base? Meaning, can I write those both as 2 to some exponent, perhaps? 2 already is like the smallest possible base I could write. But 16, what if I represented 16 as 2 raised to some exponent? Can any of you think of how I could rewrite 16? That's 2 to what power? That's 2 to the 4th, isn't it? We had one earlier where we knew that. So check it out. I'm allowed to just rewrite this as 2 to the x minus 3 equals 2 to the 4th. Because isn't 16 the exact same thing as 2 to the 4th? That's not changing the value of it. It's still the exact same thing. And so that's where you have to think a little bit, rewriting it in a smaller base. Now that they're both 2 to some power, I can cancel out the bases. Just set those exponents equal to each other. So we can see, oh, so x minus 3 has to equal 4. So x is 7. Now on the right, we've got 3 different terms. And if I look at just the bases, if I look at a 3, if I look at the 9, and I look at the 27, just look at those. And what's the common base that I could write all 3 of those in terms as? Like, what's the common smallest base for each of those numbers? 3. Can I write each of those numbers as 3 to some power, 3 to some exponent, 3 to some exponent? This first one on the left, 3, is already the smallest base that I could represent that number as. 3, you can't go smaller, right? It is 3 to the first. But 9, how can I write 9 in terms of 3 to an exponent? Isn't that 3 to the second power? But look what I'm doing. I intentionally wrote this with like little parentheses around just the 9. The x is still outside of the parentheses. So I'm replacing just the 9, right? That x is still out there. The 9 is just being written as 3 to the second. It's still being raised to the x. So I'm going to have to multiply those 2 together in the next step. Same thing with 27. The 27, hey, 27 is 3 to which exponent? The third, right? 3 cubed. But it still has an x outside of those parentheses. So I'm just replacing the base in parentheses with that smaller base to an exponent. Now I've got a couple parentheses. We're going to need to simplify that and rewrite this as 3 to the x plus 4 equals, when there's parentheses, how do I combine those exponents? Do I add them or multiply? We're going to multiply. So that's 3 to the 2x times 3 to the 3x. All right, so I had those parentheses and I just multiplied their exponents together. At this point, this is just like an earlier problem that we had. The left side is still 3 to the x plus 4. The right side, if I'm multiplying the same base, I add the exponents. So that's the same as 3 to the 5x. And we finally rearranged this problem, rewritten it, so that now we have the same base on each side written just one time. Now we finally got back to that point where I can just ignore the bases and set those exponents equal to one another. So we say, hey, x plus 4 has to equal 5x. Subtract an x from both sides. 4 equals 4x. So x has to equal 1. Quite a few steps in that problem. But none of those steps were actually that difficult. It was just combining a whole bunch of little skills that you've learned over the years. And we're just putting them all together. But just take one little piece at a time, and you can solve any of these. You all are more than capable of doing this, for sure. Anyone want any clarification on any of those steps? Want me to scroll up or anything like that? Something you want me to go over again? I'm happy to right now. All right, that's a big concept, rewriting each term with the common base. All right, let's try this one. 4 to the x equals 8 to the negative 10. Seems easy enough. Now remember, we want to write these in terms of the lowest common base. And some students at this problem would think 4 right away. Oh, write them both in terms of 4. But is 8 the same thing as 4 squared? No. So our common base isn't actually a 4, because 4 to the second isn't 4 times 2. 4 squared would be 4 times 4, which is an 8. So I need to go even smaller on both sides. So you want to rewrite both of those bases in terms of 2, because I can write 4 as 2 squared, and I can write 8 as 2 cubed. Remember to keep that base in parentheses. So you're going to write 4 as 2 squared to the x, right? I'm just replacing the 4 with the 2 squared. The x is still kind of like outside those parentheses. 8 is 2 cubed. But outside the parentheses, I've got this negative 10. Now, when you have an exponent raised to an exponent, you multiply those exponents together. So this will be 2 to the 2x equals 2 to negative 30. Now they're both the same base of a 2. Ignore those 2's. Set the exponents equal to one another. So 2x equals negative 30. Divide by 2, and x is negative 15. We still have quite a few problems to go through, everyone, so I wouldn't pack up yet. You're going to see more problems, more difficult, that I've got in the next couple slides. You should probably wait till the bell rings this time. Or every time. That's what I'd appreciate. But just for your own knowledge. You can pack up when the bell rings, if you think you've learned enough. All right, this is just another one. You're going to go to the common base of 2. So if you think about it, if you're like, okay, I know 2 and 4 can be written as a 2, but 32, if you're not sure about that, just keep on taking 2's and multiply them over and over again, see if you get to that number. So look at what one common base is, and everything will be able to be written in that base. Same thing. So we're not going to go through this right now. Same as that last one. I'd write them all as 2 to some power. All right, here's where things are going to get a little tricky. I know, scary, right? If I'm looking at my bases, I have 100 and a 1/10. What would the common base be? 10. I can write this as 10 squared. How can I write 1/10 as 10 to some exponent? Negative exponents. Remember how negative exponents flip the fraction? So I'd write this as 10 to the negative 1, because that would flip it into the denominator. You're going to see problems like this on your homework tonight, okay? Then you just multiply them with the other exponents, set those exponents equal, and solve. Some of these homework problems tonight, you're going to have quadratics. So write it in standard form and factor it, and you're going to get 2 x values. That's not too scary, right? Yeah, so I want to make sure I got to this point. Should be the last one. All right, bye, everybody. See you later.